You. Welcome back, everyone, from your slightly extended break. One more lecture for today. Again, talking about rheometry. We're going to review the practical applications of rheometry. First, my reminders to enter your questions for the instructor at the bottom of your screen under the Q&A feature. That also, we will once again do one more poll at the end of Mr. Clark's lecture and ask you to respond to that. And then my typical warning. Please be reminded that the lecture content being presented today is the property of the instructor. Unauthorized recording of the presentation is prohibited, and the use of any material must properly acknowledge both the event and the instructor. And with that, let me introduce our last instructor for the day. Mr. Ross Clark was recently retired from CP Kelco, where he was Distinguished Research Fellow for 40 years. He led a group that screened for new food hydrocolloids, which ultimately led to the food approval of Gel-An gum. Besides enjoying his retirement, Ross does occasional consulting work in food science, rheology, and sensory evaluation.
Okay, well, it's pleasure to be able to speak with all of you today and talk about some of the practical applications. As you heard, I had a long career at CP Kelco and worked with a lot of different hydrocolloids and a lot of different applications, and you're going to hear about some of those things here. Let's see here, let's get to the next slide. So we're going to divide this really into two parts. We're going to talk about how rheology solves problems. I'm going to go through 4 different areas on that, as you see on the slide. Then we're going to spend the last part of the talk about suggestions and how to avoid making mistakes with rheology. And unfortunately, I see quite a few of those, and I'd like to make sure that everybody that's on this call avoids those. So, hydrocolloids and rheology. Most of the commercial use of these materials rely on their rheological properties. And because of their large molecular size, they have entanglements, associations, and crosslinks. Those things kind of overlap with one another. But let's play this little video here, and you're going to see a solution being poured into a beaker, and then I'm going to agitate that beaker. You see the little marker particles in there, some spices, and as you rotate this, it does a remarkable thing. It shows recoil. And how does it do that? Well, it does that because of all the entanglements that are going on in there. So entanglements simply means the hydrodynamic volume of the molecules overlap. Associations means there's something about that molecular structure, a functional group, some aspect of it that creates a tendency to stick onto its fellow molecules for a fairly short time scale. And cross-links means that they form associations between these molecules that last for a long time. Understanding this structure-function relationship is key to application of these materials, and matching what the application requires to what the different materials, their properties they possess, is the secret to success in successfully stabilizing things. The first thing I'm going to talk about has a fairly long history. Inkjet printing first began with that little HP 2225 you see down there back in 1984. And that was the first time that people actually shot out drops of ink, and it landed on paper in this case, and they created printing. So you have one or more moving print heads that turn on and off and deposit drops of ink onto some kind of material. It can be paper, fabric, carpet. These days, inkjet printing is used a lot for lot numbers, date codes, and things like that on boxes. If we're going to do this, we need a fairly fast cycle rate. We obviously want to be able to turn these jets on and off very quickly. That gives us print speed. We want to be able to control the size of the drop, and that is what gives us all the subtleties in shading and good color reproduction. And we want really small, accurate drops, and that's what's going to give us definition. And of course, we need compatibility with the media and the dye or pigment that we're going to be depositing on that media. So inkjet printing has come a long ways over the years. This photo shows a print head for carpet, and that print head is moving to the left. It has turned off with this bar that you see over here. It's just finished printing this, but unfortunately it's got this little tail, and that's going to fall on carpet that wasn't supposed to be printed, and it's already turned on and started firing here. So we clearly have a problem that's going on here. And some of the problems you see in carpet printing look like this, that we might suffer from poor definition, where the white unprinted carpet is, and this red thing is intruding into both the gray printed area and this. So we're suffering from a lack of definition. In this side view of carpet, we've deposited the ink on, and it's gone all the way to the base of the carpet, and it's leaving these top kind of gray hairs here on the top of the carpet, which you see over in this other slide, which is called frosting. Better, we'd like to very well control the penetration, so we have a very dark carpet. We've made the most use of our expensive pigment or dye, and we leave this bottom area unprinted. And because nobody's ever going to wear the carpet down that far. So we need to control definition, penetration, and we don't want to see this frosting. Well, how do we do that? Well, these two graphs that you see here first show what the shear viscosity is versus shear rate. And I've shown the green curve, which shows good printing, and the blue curve that shows good tailing. Well, if you measured in shear viscosity, you might say, well, it's that presence of that high viscosity there. The samples really are not that different. If we measure extensional viscosity, and Blake talked about that a little bit in the next slide, I'll explain one way that can be measured. If we measure extensional viscosity, well, now we see there's a day and night difference between the two. The one that shows good printing is relatively lower in extensional viscosity. In fact, at low extension rates, it's an order of magnitude lower. And it is relatively constant with extensional viscosity, whereas the blue one that shows tailing is not. So a day and night difference. And if you didn't know to measure extensional viscosity, you wouldn't be able to predict tailing. How can you measure extensional? How can you pull on a liquid? It seems completely illogical, completely impossible. Well, this was an instrument that was developed with a company called Rheometry, and a friend of mine, Jerry Fuller, up at Stanford. And it uses two opposing jets submerged in a beaker of liquid, two syringe pumps that suck the liquid out of the beaker. And this is a close-up of those two jets in cross polarizers looking at birefringence. And so we see the pore fluid doesn't know whether it should go in the left jet or the right jet. And in between those is an area of intense alignment, which is why it's bright colored, because it's birefringent, and it's getting stretched. And we measure the force and the volumetric flow, and we can determine extensional viscosity. Unfortunately, there aren't many instruments around. This instrument was designed a long time ago, but extensional viscosity, you're going to see in a couple other places in my talk, is really, really important. And it's always 3 times the shear viscosity at a minimum. And for many materials, it can be 1,000 times. And when we get into showing some of the fire retardants, we'll show examples of that. So extensional viscosity, a very important attribute. Well, let's talk about penetration and definition. We're measuring elastic modulus as a function of frequency, a so-called frequency sweep curve. And we see here that the one in red, that line, that shows poor penetration. The orange line, well, that shows poor definition. And Goldilocks, the green line right in the middle, that balances penetration and definition. So again, you need to know this in order to be able to correctly print that carpet. What else do you need to know? Well, if you're printing carpet, the carpet is steamed, it's heated in order to set the dye. And you might get everything just right. You might have your elastic modulus right where you think it needs to be, but then you discover you're still getting lousy definition. Well, that's because as you heated it in the steamer and it came up to 85 degrees, all of a sudden you don't have the elastic modulus that you thought you had, and you end up getting poor definition. So if we're going to do good printing, and the little shot, the little picture that you see, there's one example of things you can order up online now. You send them a JPEG or other photograph, and they send you back a carpet or piece of fabric printed with whatever your design is. So if we're going to get good inkjet printing, we need to control the extensional viscosity, not too high. If it's too low, the droplets break up. We need to control the elastic modulus. Too high and we don't get good definition, or don't get good penetration. Too low and we don't get good definition. If we control the thermal stability properly, we won't lose this if it's a material like fabric and carpet that's heated. And none of this stuff gets measured with what the industry thinks they're controlling their print paste with, which is the Brookfield Spindle Viscometer. And we're going to have more to say about that later. Okay, let's shift gears and talk about food. You know, syrups and toppings, these are relatively high sugar systems that we enjoy putting on our waffles, pancakes, and ice cream and things like that. Well, to reduce calories, a lot of times they add carbohydrate thickeners, and that gives more body when they've pulled the sugar out. But unfortunately, these things then can get stringy and have long flow. And that's messy, and consumers don't like it. So how do polymers influence this? Well, here's another photograph, and this shows on the left carboxymethylcellulose, otherwise known as cellulose gum, and Keltrol, xanthan gum, and CMC blended together. And you can see that the syrup that only has the CMC or the cellulose gum has a longer flow than that with the xanthan gum and the CMC. In fact, in this photograph, I caught a really nice example of forming satellite drops. And again, we're going to see a video of that later. So if we measure the extensional viscosity in the syrup, we see that the xanthan gum drops in extensional viscosity. It's extensionally thinning, whereas the CMC is extensionally thickening. And it's that extensionally thickening characteristic that causes it to have long flow. And why is it extensionally thickening? Well, it's what's called a random coil polymer, and that's a very flexible polymer. And as you pull on it, it actually expands its hydrodynamic volume and thus increases its extensional viscosity. Xanthan gum is a more rod-like or worm-like chain, and therefore it does not expand its volume. If we'd looked at these in steady shear, well, what would we have taken from this? How would we have been able to predict which one was the more stringy flow? Because we see the xanthan gum is a more pseudoplastic. The viscosity drops with increasing shear rate. The CMC, the cellulose gum, is showing this typical random coil performance. You really wouldn't have been able to predict it. So if we're going to formulate a syrup that requires that we have the viscosity high enough for good cling, well, we can do that with either gum, but the xanthan's going to pour more easily. But we need to control this extensional viscosity, and we need something that thins at high extension rates and doesn't thicken. And a lot of times, if you look on the label, you'll see these things use both xanthan and CMC. The video that's playing here shows an oil and water emulsion breaking over about a 3-week period of time. So we'll let that play while I explain that all colloids are inherently unstable. Commonly used stabilization methods fall into one of 3 broad categories. You change something about the surface. You inhibit coalescence by putting an emulsifier or something else like that. You might stabilize it with zeta potential and use electrical charge to keep the particles from compacting. Or what I'm going to be talking about, rheological control. You make the continuous phase thick enough that you slow things down. And in that case, stabilized just simply means that we didn't have an objectionable change over storage. But if we're going to predict colloidal stabilization, we need to know one thing. We need to know what is the shear rate that occurs during destabilization. So we need to know the shear rate around a particle as it falls. So that all began, and Blake talked about yield stress. And a lot of people refer to yield stress as the force required to get a sample moving. So a lot of people said, well, xanthan stabilizes these things because it has a yield stress. So I went over to a controlled stress instrument and I applied the smallest stress that it could apply. And I measured the resulting strain, which is the red curve, the amount of movement. And then you take the derivative of that, the shear strain rate or the shear rate is blue. And if you're really patient, and I am very patient, you wait 12 hours and you see, no, with the smallest force we could apply on that xanthan gum, it flowed. It flowed. So it doesn't have a yield stress. So it's not yield stress that's causing it to be stable. So we're still going to probe and we're going to ask ourselves, what is it what is the shear rate around that falling ball? So I took a bunch of those creep curves, linked those together, and what do you see? At this stress, we got this rate and we got this viscosity. And we see that at very low rates, we're getting these constant viscosities in these creep tests. So you do a whole bunch of those. This one went on for 16 hours. So to get all this data took 16 hours. To be a rheologist, sometimes you need to be very patient and wait for your sample to do its thing. So we took all of those creep curves as well as some other data we generated, and we created this 9 orders of magnitude of viscosity versus shear rate. And Blake, again, he showed that graph that showed viscosity, shear rate. And we really needed this data because we're going to build a model here. And that's what's coming up next. So we've got all of this flow curve data. And now we dropped our particles. We dropped our model particles, which are glass and ruby balls of different sizes. And we dropped these in a bunch of different xanthan gum concentrations. And we determined viscosity using Stokes' law. And this little cartoon is up here to remind you that we're trying to understand these streamlines as they flow past this particle, or the particle falls through the media. It doesn't really matter dimensionally. And we want to know what's the shear rate around this, because Stokes' law tells us what the viscosity is based on gravity, the size of the particle, the density of the particle, and the fall rate, but it does not tell us what the shear rate is. Okay, so here's a table, and we collected all of this fall rate and all this Stokes viscosity, and I promise you this is going to lead somewhere interesting. And where it's going to lead is, we took that one ball and one thing, and we got 2100 was the Stokes viscosity, and we came across here, and we came down and we said, based on that flow curve that we collected from all those creep curves, we came up with what the extrapolated shear rate was. I looked at a bunch of this and it became very obvious that the theoretical shear rate could be mapped by the velocity of the fall divided by the diameter of the particle. Proof of that is this correlation. So this is across many, many, many different balls, ruby balls, glass balls, many sizes, many xanthan concentrations. Now we know when we drop a particle, or when the emulsion separates, or when a particle settles, we know what the shear rate is around that particle. Let's do something with that. So here's a little story problem. Assume we have a drug suspension. That drug has a 2.5 micron size. It has a density of 1.25. We can have it separate 2 millimeters in a year, and we think that's sufficiently stable. So we go through and we calculate the velocity. From that V over D, we calculate the shear rate. From that shear rate, we can calculate what viscosity we need to hold it up, and that translates back to about a 0.3 xanthan gum solution. Now you'd say, well, that's a lot of trouble to go to, except that I can now predict using a test on a rheometer. And even if I take 2 or 3 days, I can predict what's going to happen in a year of storage stability. So stabilization is conferred by viscosity at very low rates of shear. Once I know all of my criteria, I can predict this. And it's so powerful. If you've ever had to do stability studies, if I could tell you, I will tell you what's going to happen in a year, and give me just a day and I'll predict that. I think you'd find that rather valuable. This takes new approaches. It isn't the way that people always approach this. and we can predict stability very effectively this way. The last application that I'm going to talk to is near and dear to my heart, living in California and living very near where we've had some of these fires, too near sometimes. Fire retardants are something that it's all too common to see these airplanes dropping this pink red stuff out of the back of the plane, and that's called Phos-Chek. It's a phosphate salt that's used to treat brush fires. It does that by reducing the cellulose char temperature. It also slightly dampens the fuel, and that makes it harder to burn. If you ever are unfortunate enough to be close enough to watch this, you'll notice the pilots drop it where the fire is going, not where it is. They never drop it on top of the fire. It's usually delivered by fixed wing aircraft or helicopters. And when you make these materials up, you've got a very limited amount of time. I've been there and done this, and they don't want to keep that plane on the ground very long. And we're going to talk about the delivery pattern and the cling here with some videos in a second. So I call this my flying rheometer, collaborated with the California Department of Forestry on this. And so this is the biggest rheometer that I've ever used. So let's go to the next slide, which is going to be 3 different shots of planes flying towards us. And those planes are going to drop fire retardant, which is what they're doing now. Now, what you want to look at is you want to watch as it hits this field full of we had a bunch of Cool Whip cups set up on posts out there to measure the delivery pattern of this. You want to look because we want that stuff on the ground as quickly as we can get it. So let's look and see what happens as it falls out of the airplane. We see the unthickened one over here. Well, this stuff's just hanging in the air. It's evaporating. It's not doing any good. This thickener did a great job, and this thickener is not quite as good, but still much better than the unthickened case. So that's an example of how you deliver a fire retardant effectively. Now, let's go to the next slide, and let's look at what this poor fluid has to put up with as it leaves this airplane. So we're flying along parallel to this plane, and he's doing a drop. And you see that the fluid leaves the front of that plane, and it's in a fairly big chunks, basketball-sized chunks. But as it's subjected to roughly 100 knots of airspeed here, it gets torn into pieces. And those pieces are what have to fall into that previous shot that you saw. Those have to fall and land and be as integrated a piece as is possible to do. So it's a very difficult job what we have here for the fluid. Now, we need to think about what happens when it lands on the ground. So we're going to look at 2 different fluids, just a little drop falling on this dowel rod that you see here. And we're going to look at what happens to those. The first one has a very high Troughton ratio. That is, it has a lot of extensional viscosity compared to the shear viscosity. And let's watch the little dance that it does as it falls. So this liquid, now you can really see what extensional viscosity is. And if you watch in this area down here, you're going to see a fascinated behavior because this very elastic fluid is going to create satellite drops. And just watch right here as those drops, it gets thinner and thinner, and they just slam back together into one another, which they're about to do right now. So it's amazing some of the elastic properties of these liquids. But what happened? That liquid, if this had been on this dowel rod, if this had been a branch or something, I would have very effectively coated it with a nice layer of fire retardant. Let's look at this other one, which has a much lower Troughton ratio. And while it does kind of a pretty dance as it falls, it is not nearly so effective at coating that branch. So that's a little bit about what it takes for fire retardants. They have to build viscosity very quickly. you can't keep that airplane on the ground for more than 15 minutes. They really want it back up in the air in 10 minutes. It must resist breakup when you drop the thing. As you saw how the air tears at the fluid and tears it apart. It needs to cling to the fuel sources. Anything that lands on the ground, that's wasted. It's not going to put out keep the brush from burning if it's on the ground. Of course, it can't damage the environment. The phosphate salts, in effect, serve as fertilizer for next year's growth. And sometimes these areas that are burned come back even stronger the next year. And of course, because we're going to be covering huge acres, it can't be a very costly material. So that's kind of what it takes for fire retardants. That's the application section. We blasted through 4 of those very quickly. And I think you can see from each of those, we pay very strict attention to rheology. We pick different polymers based upon their degree to associate, to have extensional viscosity, to create an elastic modulus, to have thermal stability. So now we're going to talk about some different types of measurements. Blake already covered that to a certain extent, and a couple of these slides are actually going to be repeats that were used in his slide, but let's go through some suggestions and so on. So a lot of the errors that I see people make, and when I review papers, a lot of times when people are not been formally trained in rheology, they make these kinds of errors. And let's make sure that all of you that are on this talk today don't make any of those errors. So those Brookfield viscometers, those spindle or index type viscometers, a lot of times those mislead you. And we've got some videos to show that. Blake talked about Couette and cup and bob corrections, and we're going to briefly touch on that because he already covered it. Don't improperly fill your test fixture. So here we see cone and plate that's underfilled. There's a little curve in, overfilled, and the Goldilocks one that's filled just right. You can't have evaporation if you're doing some of these tests like I do that might go on for days. You can't have evaporation and skin formation at interfaces. And one way to always test that is go take some latex paint, throw it in your rheometer, use your evaporation control method. For me, most of the time, it's a very thin layer of silicone oil at the interface. And see, can I keep that latex paint from drying and skin formation for a day or so? If I did, whether it's cone and plate, Couette, parallel plate, then I know I have good evaporation control and I'm not getting an error. I highlighted this next one, which is choosing the wrong measurement. Boy, do I see people run flow curves and they got viscosity, shear rate, and they think they're going to explain everything in the world from that. From some of the earlier examples I gave you, I think you can see why a flow curve is oftentimes not the best measurement to be publishing or trying to characterize a material with. Ask yourself, where does the viscosity come from? Again, Blake touched on that. Does it come from associations between molecules? Does it come from suspended solids that are present there? Do I have a random coil polymer? Do I have a very stiff polymer? Do I have branches in it? All of those things change the rheology. And at the very bottom here, what have I put? I've said, following previously published work without a question is the most common mistake that I see. The fact that it made it into a journal does not make it something that's worth repeating. And maybe I'm an old codger about that, but I certainly see stuff that gets put in the literature that I think is misleading lots and lots of people. And I don't know how it made it past some of the reviewers, but it has. Okay. Let's talk about these spindle viscometers, because no doubt you're going to encounter these as you work with rheology. These things are, Brookfield is a great example. They're found in many labs, and oftentimes they're written into specifications. ASTM specs and many other things use those. The problem is they don't have a defined shear rate, and you can't necessarily change spindles and speeds and get the equivalent viscosity. So that is a real problem. And some spindle numbers are available from the manufacturers, both a disc and a cylinder. And I'll show you a video of that in a second. To their credit, they're easy to use, they're relatively cheap, but they also have attachments. They have proper attachments for these things called small sample adapter, ultra low viscosity adapter. These things can be put on these and we can make them into proper instruments. So spindle viscometers widely used, but they've got their flaws. So let's look at what some of those flaws might be. Again, Blake showed you that diagram, and I'm going to share it again too, of what happens in Couette flow. But let's take a spindle in a carboxymethyl cellulose, a relatively non-pseudoplastic material in xanthan gum. And can you see what's happening there? That all of my marker particles are flowing. I'm getting that sort of laminar flow that we need to get in order to accurately measure viscosity. And let's take a look at that xanthan one again. Wow, it's really only flowing next to the spindle, isn't it? So obviously these can't be the same shear rate. Not all the volume of fluid there is seeing the same rate of shear. It gets even worse if we look at what goes on with a disc-shaped spindle that you see over there on your left and what you see with this spindle. Now, I put some dye in this, and this experiment went on for, I think in total, it took about 15 minutes. And we're supposed to be evenly shearing this sample, but look what's happening. The dye is really only staying in the top. And this was a simple material. This was glycerin water. And these flow patterns become horrendously complicated, not at all what we want. And so these, I can't emphasize enough, if you haven't gotten it by now, these things can really mislead you because they do not have a constant rate of shear. This was the diagram that Blake showed. And it's looking down on that spindle, and it's looking out at that outer wall, and we're seeing these dots that represent marker particles. If the material is Newtonian and we've got laminar flow, that is, each layer moves the exact same amount compared to the other one, well, we end up with this very linear profile. But with pseudoplastic materials like that xanthan gum, look what we've got here. Most of the flow occurs near the rotating member, and that is a real problem. This is, again, another version of that same slide that Blake showed. There's a beautiful correction developed all the way back in the early 50s by two guys at Case Western, Krieger and Elrod. And they are legend for figuring out this problem now 70 years ago and solving it. How big is that error? And again, Blake briefly touched on this. Well, if I've got a wide gap, like I showed in that video, and I've got a very pseudoplastic material, I might miss my correct shear rate by over 100%. Only if I have a very narrow gap do I have minimal errors. Now, the DIN standard requires the cup-bob ratio to be greater than 0.92. So this would meet the DIN standard. However, if I throw a very pseudoplastic material, even in a proper rheometer, like the Anton Parr MCR 300 that you have there in Virginia, I will still end up with as much as a 15% error. So it's something to bear in mind, and people make this mistake all the time. Okay, enough about negativity and enough about mistakes. How do we choose a measurement? Well, let's ask ourselves, why are we even bothering? Why are we walking into the lab? Why are we making a measurement whatsoever? Well, we might be trying to produce or predict something about the end use. And that was the way I spent a lot of my career at CP Kelco. But we might also be trying to understand sample differences. Maybe we made a change to the polysaccharide that we were making. We want to understand structure-function relationships. What happens if I make a molecule more flexible? What will occur in shear, in extension? What will happen to the elastic modulus? So I might measure in order to understand that. I might be characterizing for a patent, for intellectual property or publication. So those are reasons that we measure. What kind of things change the rheological properties? Well, obviously temperature does. Thick as molasses in January is a statement we've all heard. The length of time that I shear something, do I mix it for just a second or I mix it for an hour? Those are going to result in a change in viscosity. Obviously the shear rate matters. That's what we've been talking about with pseudoplastic materials that some people refer to as shear thinning. By the way, a little editorial comment. I never use the word shear thinning. Why don't I use the word shear thinning? Because do I mean it shears with rate? That's pseudoplasticity. Do I mean it shear thins with time? That's thixotropy. So if I just say, oh, it was shear thinning, do you know whether or not I meant thixotropic or pseudoplastic? No, you don't. And so we don't want to confuse things by using imprecise language. We have words, pseudoplastic and thixotropic, to address that. So anyway, the rate of shear affects it, and the amount of shear strain applied affects it. Blake showed you a strain sweep. A strain sweep in viscoelasticity measures the linear viscoelastic region. Very, very important to know. Let's say we've constructed two molecules and that they've got some entanglement, an association point. And in one case, that point is very dense. They're very close to one another. In another case, it's further apart. I have unsubstituted regions further apart. Well, that one with the long regions is going to show much more tolerance of applied strain. It's going to be have a longer viscoelastic region than something that has entanglements and association points much closer, and there's less backbone to take up that strain and accommodate it. So modern rheometers, like your MCR 300, can do more than a dozen tests. And it breaks my heart every time I walk into a lab and people have it kind of locked into one particular test, especially a flow curve. And they don't change the way the instruments run. They don't even change the parameters. So seek advice or learn more about rheology than I can teach in an hour, and pick one of those measurements. You're going to learn a lot about your sample. So we always start with temperature because, of course, temperature affects all of these things. And who says that what you do at 23 degrees is going to relate to somebody using it at 37 degrees? So we need to measure that because we know rheological properties change with temperature. You need to pre-shear. That is, if there's any thixotropy in your sample, shear it for a minute or two before you begin your temperature ramp test. And when you do a temperature ramp test, I like doing them at 10 reciprocal seconds and scanning at least plus and minus 20 degrees. And the Couette tool, the cup and bob with a little bit of silicone oil on the top, is the ideal tool. Don't ever use a cone and plate because as you heat up the sample, that gap between the cone and plate will change and your measurements are going to be garbage. So steady shear measurements. We need to know, is our sample thixotropic? Does it change with the amount of time that we shear it? So I like a step rate test. I go from a low rate to a high rate and back to a low rate. And I usually go 0.1, 1,000, 0.1 reciprocal seconds. If that variation on that second 0.1 test is more than a few percent, you need to characterize thixotropy. And that's an important aspect of samples. It's actually a very valuable property of many thickeners. Well, then you step in and you're going to run this flow curve that everybody is sort of required to do, it seems like. Run your flow curve from high rates of shear to low. Again, I see so many people, they start at the low speed and they go up to the high speed. And that's not a good idea because if there's any thixotropy in your sample, it's going to interfere with your measurement, which you were trying to measure, pseudoplasticity. So it's more accurate and it's faster. So if I go from a high rate to a low rate, I've already developed my flow field. I can run the test in a fifth the time if you run the test from low speeds to high speeds. So what about this thixotropy? It frustrates people. I've had a lot of people come to me and say, I tried measuring my sample, it keeps changing. What is the correct measurement? Well, that sample is trying to communicate to you. It's trying to tell you something. And so you should listen. And you do these step rate tests, you characterize the thixotropy, because that time dependence is telling you a lot about the structure that you don't necessarily learn just from shear rate dependence. And you really want to measure the recovery of thixotropy. It's just as important as the breakdown. So again, Blake touched on this. What about this whole thing of viscoelasticity and applying an oscillatory, a sinusoidal deformation? Well, that's mostly useful for understanding what's going on. What's the molecular structure? What strain dependence, what frequency dependence do I have? So that tells me what my molecules are doing. So if you're really looking at this and you want to synthesize things, or you want to isolate different materials, and you want to really understand what is going on inside, there's no better way to probe that than to look at the strain and time dependency of these associations. If your frequency sweep is, your G prime curve is very flat, well, that's telling you your entanglements last for a long time. This point on here about, and I think this is, it bears mention again, please don't use hertz for frequency. That is the unit that frequency is most often expressed in. But there's something called the Cox-Mertz relationship that's been established for eons. And it says that if I measure in radians per second, not cycles per second, in radians per second, so a difference of 2 pi. If I measure in radians per second, my frequency relates to my shear rate in reciprocal seconds. But that only holds if you measure in radians per second. So any well-trained rheologist always uses radians per second and not hertz. And of course, time temperature superposition is a great viscoelastic tool to be able to extend the range of frequencies that I can measure. So it is a big benefit of viscoelasticity. What are the most overlooked tests? Well, creep and recovery. And you apply this constant stress, you monitor strain. We showed how that measures very low shear rates. Blake showed a slide of how you can transform creep data into frequency data, providing the strains within the linear viscoelastic region. And it's the best way to get low shear rate data. There's also another test called dynamic after shear. So I apply a steady shear, and then I ask the rheometer to just bang, instantly go into a dynamic test, and I watch the recovery of G prime. Boy, can that tell you a lot about how your molecules rearrange and reform their associations. Another very overlooked test that Blake just started touching on is the use of these models. And we construct these things with springs that represent an ideal Hookean element and dashpots that represent an idealized viscous element. And those can be hooked in series and in parallel. And with this 4-element model that you see here, and we take a creep recovery curve, we can assign values to each of these. But why do that? Well, a lot of times there's physical significance to that. If you're looking at a gel network, one of the things may represent the strength of the bonds between your polymer chains, and another one might indicate the migration of solvent between those chains or percolation. So fitting data to a 4-element model is super useful in understanding a lot of what goes on in the real world. The most questionable measurement, and boy, do I really question this one, is the point where G prime and G double prime cross. By the way, I've got 2 G primes up there. One that should be G prime equals G double prime. That gets thrown around a lot. And all it means is those things were equal magnitude. It's easy to determine. Software oftentimes will determine that for you. The phase angle happens to be 45 degrees there. It does not mean the relaxation time. If you go through and you determine relaxation time properly, you'll find that the crossover does not. But it's overused, it's been published, and unfortunately, it's one of those things that's gained traction. And I think I'm fighting a losing battle for people to quit calling it relaxation time. But that's a very questionable measurement. So let's wrap up. You've got there at within your center, you've got a MCR 300 that you recently took delivery of. It's a beautiful controlled stress and strain instrument. You've got Couette parallel plate, cone and plate tools. It's got great temperature control, can measure steady rates over a wide range, and it's got a very wide range of dynamic and frequency frequency and strain capabilities. So it's a great tool. Like I say, it can do more than a dozen different tests. Setting those tests up, setting the parameters is intimidating if you're not a rheologist. But that's why the world's full of people like me, rheologists, because we stand ready to help you. Now, before you ask me questions, I want to throw one at you. What you see there on the screen is a drop of water that I dyed green. Going to fall into a beaker full of uncolored water. We know it's going to splash. What's going to come out? Bulk water from the beaker or the same drop that went in? So let us play the video, the last video I've got, and we see it's pretty much the same drop that went in. So isn't that interesting that you would think that it had mixed and blended in with all of that other water, but in reality it didn't. So I hope this talk has let you see the wonderful world of rheology and how it can be used in applications, how it can be used to characterize materials. And I hope that you guys have got some questions to ask me.
That was fantastic, Russ. Thank you very much. Okay, folks, your poll has popped up on the screen, and as you can see, Lauren Mills has joined us again, and we do have at this point a few questions. It says one, but it's a multiple part question. So Lauren, if you're ready, you may take it away, and anyone else who wants to ask, please go ahead and type your questions in for Ross now.
Okay, so first, are there any methods other than using low viscosity oil you can recommend to prevent solvent evaporation during cone and plate or parallel plate measurements?
Okay, we'll address that one. There are a lot of mechanical devices that rheometer manufacturers have made, and it involves controlling the atmosphere over the cone and plate or couette. I don't use those in a lot of cases because those require some evaporation to occur, but people have put dampened paper towels and so on around there. If you're dealing with a very volatile solvent like acetone or something like that, it really becomes problematic because you might have a solvent where it's not possible to use something like silicone oil, but you're looking for something to put on that interface that will not mix with your continuous phase, whether it's aqueous phase or a solvent. So it's really best to try to cover that edge up and not use these sort of mechanical devices that the manufacturers offer.
The next part is, how would I know if evaporation or diffusion of oil has affected the results?
Okay. Again, for a water-based material, that's why just plain old house paint. Go buy some latex paint, fill your rheometer full of latex paint. It'll wash out, don't worry. It's not going to stick to stainless steel. And use whatever method that you have. And if you cannot keep that paint from drying for the same length of material that you're going to be testing, then you know your evaporation control is not working. So that is the best test that I've ever found because what actually happens, what we're worried about is forming a film at that interface. And there is a whole branch of rheology called interfacial rheology. We're not trying to measure that. We're trying to measure bulk rheology of your sample. We don't want that interface getting in our way. So use a material that's going to form a film. See if you prevent that film formation. If you have, your system's adequate.
And then the last part, any tips on sample trimming for correct sample filling on a Peltier system?
Yeah. The best tip I can give you is to make sure you use a positive displacement pipette. We all have in the lab these air displacement pipettes, and air displacement pipettes are fine if you're putting enzyme or something into a reaction. They're tremendously accurate. On the other hand, if your material is thick and viscous, those things don't work. And so you want to get a positive displacement pipette. There's a number of those on the market. That positive displacement pipette is going to deliver exactly the volume that you need, and you'll make sure then that you don't have to trim, that you've actually put the correct volume in there. And every instrument that I'm aware of today in the tool setup will actually give you what the correct filling volume is. So use a positive displacement rather than an air displacement pipette.
Okay, so thank you for that set of questions. Does anybody else have any questions of Ross before we adjourn for the day?
Oh, you guys are too easy on me.
They are. I'm a little saddened.
Oh, there's one. What are typical volumes that you work with on these rheometer devices? How much can you miniaturize a rheometer to study, for example, a sample derived from a biological source that may be of limited quantity?
Fantastic question. It really is. If I go to the smallest tool, which is typically a 25 millimeter diameter tool, so just about an inch, and if I use parallel plate geometry instead of cone and plate, and that's a bit of a sacrifice, and we didn't talk about that. I mean, God, the field of rheology, I spent years being trained, and we're trying to do this in an hour. But a parallel plate, 25 millimeter diameter, I can measure as small as 1/10 of a milliliter. Now, if you need smaller still, there's a company called Rheosense that makes a micro viscometer, and it is a micro channel device. It's a MEMS device, and it can measure even smaller volumes. But on the instrument there at the center, you can measure as small as 1/10 of a milliliter. So for very valuable or limited samples, that's pretty small.
Great. Okay. So I don't see any other questions at this point for Ross. I learned a lot. I used a Brookfield Spindle Viscometer in the quality control lab that I ran many, many years ago for many years. So now I get it. Thank you, Ross.
You're welcome. Yeah, they're a great index. They're not so good as a rheometer.
Well, it's what we used, and probably I would guess they're still using it. So, hey, listen, everybody, thank you very much for your participation today, for answering our poll, for your excellent questions. And we have one more day tomorrow, one more full day. And then on Friday, we're going to sit with panelists and have some further discussions as you wish. So I do hope you'll join us for the next day and a half. We will reconvene summer school tomorrow, again, 11 a.m. Eastern Daylight Savings Time, and we hope to see you then. Thank you very much. Good night.